Hello everybody. In this lesson we will study about circles, some of the definitions of circles, primarily focusing on what is a tangent of a circle and what are the properties of the tangents to a circle. So welcome to this lesson. In our previous classes we have studied about circles, that a circle is a collection of all points in a plane which are at a constant distance, that is radius, from a fixed point. So this is called the radius of the circle and this is the fixed point, the center of the circle. We also studied some basic definitions of chord, that is a line segment joining two endpoints on a circle. We studied about segments, the major segment and the minor segment, and we also studied about sectors. The region between the two radii is called a sector. Now let us examine the different situations that can arise when a circle and a line are given in a plane. Let us consider a circle and a line PQ. There can be three possibilities as shown over here. So if you observe in figure 1, the line PQ and the circle have no common points. In this case, PQ is called the non-intersecting line with respect to the circle. Now let's come to figure 2. There are two common points A and B that the line PQ and the circle have. So the line PQ and the circle have two common points A and B. In this case, we call the line PQ as the secant of the circle. Let's come to case 3. There is only one point A which is common to the line PQ and the circle. In this case, the line is called the tangent to the circle. So these are the only three possibilities that there can be between a line and a circle. Either the line is a non-intersecting line to the circle, or it can be a secant to the circle meeting at two common points, or it can be a tangent to the circle where it meets the circle only at one point. So these are the only three possibilities. So we can define what is a tangent to a circle. A tangent to a circle is a line that intersects the circle at only one point. Just to add to your information, the word tangent comes from the Latin word tangere, which means to touch, and was introduced by the Danish mathematician Thomas Finneck in 1583. Just keep in mind. Let's try to prove this theorem. The tangent at any point of a circle is perpendicular to the radius through the point of contact. We need to show that OP, which is the radius, and XY, which is the tangent, and the point of contact is P. So we need to show that OP is perpendicular to XY. So let us see how we go about proving it. So what is given? We are given a circle with the center O and a tangent XY to the circle at a point P. We need to prove that OP is perpendicular to XY. Let a point Q on XY other than the point P and join OQ. So let us mark a point Q other than the point P on XY and let's join OQ. What do we observe? The point Q must lie outside the circle. Why? Because if the point Q lies inside the circle, XY will become a secant and not a tangent to the circle. But it is said that the XY is the tangent. Therefore, OQ is longer than the radius OP of the circle. That is, OQ is greater than OP. So OQ will be greater than OP. Since this happens for every point on the line XY except the point P, OP is the shortest of all the distances of the point O to the points of XY. So what can we conclude from that? OP will be the shortest distance from any point on XY. So it shows then that OP is perpendicular to XY. How can we say that? Because the shortest distance of a line, any point on a line to another point outside, is 90 degrees, is the perpendicular distance. We have seen that in our lower grades too. So since OP happens to be the shortest distance from O to the line XY, so OP should be perpendicular to XY. So this leads us to come up with some more conclusions. So from this theorem we can say that at any point on a circle there can be one and only one tangent. At any point on a circle there can be one and only one tangent. And the second part is the line containing the radius through the point of contact is also sometimes called the normal to the circle at the point. So this line XY, which contains the point P, which is contacting the circle, is also called as the normal to the circle at the point, at the given point. So what do we know? We know that the tangent at any point of a circle is perpendicular to the radius through the point of contact. So this is a very important property that we need to remember when we get to solve problems, that OP, the radius, is always going to be perpendicular to the tangent at that point. Let's try to figure out the number of tangents from a point on a circle. Now suppose, can you guess how many tangents will a point have if the point is lying inside the circle? There will be no tangents. So we have case 1 over here, that there is no tangent to a circle passing through a point lying inside the circle. Okay, can you guess how many tangents can you have for a point lying on the circle, passing through that point which is on the circle? You will have only one tangent. So we have the second case. There is one and only one tangent to a circle passing through a point lying on the circle. What if the point is lying somewhere outside the circle? How many tangents do you think you can have passing through that point? For example, over here, there can be two tangents. So we have a third case over here. There are exactly two tangents to a circle through a point lying outside the circle. So PT1 is one tangent, PT2 is another tangent. The line segment PT1 is called the length of the tangent. PT2 is the length of the tangent. And it happens that PT1 is equal to PT2. So any point outside the circle, the lengths of the two tangents to the circle will be equal. Let us prove this by applying the theorem. Let's look at this theorem. The lengths of the tangents drawn from an external point to a circle are equal. Let us prove this. So we need to prove that PQ is equal to PR, because we have been given a circle and there is a point outside the circle, and PQ is a tangent, PR is a tangent to the circle. We need to prove that the lengths of the tangents drawn from an external point to a circle are equal. So we need to prove PQ is equal to PR. So let us join PO, OQ and OR. So what do you observe? OQ is the radius, PQ is the tangent. OR is the radius, PR is the tangent. And from theorem, the previous theorem we studied, what is the angle between the tangent and the radius? How much is the angle? It's 90 degrees. So, because they are perpendicular, so we know that this is 90 degrees from the previous theorem. So, angle OQP and ORP are right angles. Now, in triangles OQP and ORP, we will consider these two triangles OQP and ORP. What do you observe? We observe that OQ is equal to OR. Why do we say that? Because they are radii of the circle. And PO is same as OP. Why do we say that? It's the common side for both the triangles. So, we know that OQ is equal to OR and OP is equal to PO, the common sides. So, what can we conclude? We can conclude that the triangle OQP is congruent to triangle ORP. How? Remember the theorem you studied in your lower grades, that in a right angle triangle, if the hypotenuse and one side of the triangle, is equal to the hypotenuse and one side of the other triangle, then according to RHS theorem, in a right angle hypotenuse side, the two triangles will be congruent. So, if the two triangles are congruent, then PQ will be equal to PR according to CPCT. So, thus we have proved that the two tangents from a point P outside of the circle will be equal. The lengths of the two tangents will be equal. So, this is a very important theorem which we will be using when we solve problems. Let's try this. Prove that in the two concentric circles, the chord of the larger circle which touches the smaller circle is bisected at the point of contact. So, we have two circles, the larger circle is C1 and the smaller circle is C2, and we have a chord AB which is a chord to the larger circle, and that happens to be the tangent of the smaller circle. So, we need to prove that AP is equal to BP. So, we need to prove AP is equal to BP. Now, observe from the figure. Let's join OP, and OP is a radius. AB happens to be the tangent to the circle C2. Therefore, OP will be perpendicular to AB. So, OP is perpendicular to AB. But again, observe in the figure, AB is the chord for the circle C1 and OP is a line drawn from the center to the chord which is at 90 degrees. So, we have learnt in our lower grades that when a line drawn from the center at 90 degrees to the chord, it bisects the chord. So, therefore, AP will be equal to BP. So, pretty simple, needs some careful observation. Let's try this. Two tangents TP and TQ are drawn to a circle with center O from an external point T. Prove that angle PTQ is equal to 2 times angle OPQ. So, we need to show that this angle is 2 times this angle. So, let us label this angle as theta. So, let us just use some notations. So, let us label this as theta. Now, so we need to show that angle PTQ is equal to angle 2 times OPQ. Since TP and TQ are tangents drawn from a point T outside the circle, TP will be equal to TQ. So, we can make a note, TP is going to be equal to TQ. Why? Because they are the length of the tangents from a point outside the circle. So, this is equal to this. Now, if you observe the triangle TPQ, what do you see? You see that the two sides of the triangle are equal. So, if the two sides of the triangle are equal, the triangle TPQ becomes an isosceles triangle. So, if it becomes an isosceles triangle, then the angles opposite to equal side are equal. So, this angle, angle TPQ, will be equal to angle TQP. So, we can make a note of that. So, angle TPQ will be equal to angle TQP. Why? Because it is an isosceles triangle. Let us label, instead of writing TPQ every time, let us label this as X. So, this also will be X. So, now in the triangle TPQ now, triangle TPQ, 2x plus theta will be equal to 180 degrees, isn't it? The sum of all the angles of a triangle. So, 2x will be equal to 180 minus theta. Therefore, x will be equal to 180 minus theta over 2, which I can write it as x will be equal to 90 minus half theta. I can write it that way also. Our x is nothing but angle TPQ, which is also equal to angle TQP. Now, in the figure, TP is a tangent, OQ is the radius. Can you tell me what is the angle, this full angle over here? It's going to be 90 degrees, because the angle between the radius and the tangent is 90 degrees. So, angle TPO is going to be 90 degrees. What will angle OPQ be equal to? Only this one. It will be 90 minus x. So, we can just have this working on the same page over here. So, angle OPQ, angle OPQ will be 90 minus x. But what is x? It is 90 minus half theta. So, we can fill in the value of x over here. 90 minus x is 90 minus half theta. Open the brackets. It's going to be 90 minus 90 gets cancelled if you open the bracket, and this is going to be equal to half theta. Half theta. But what is theta? The angle theta is PTQ. So, can I write this as, now angle OPQ is equal to half of angle PTQ, which implies that angle PTQ is 2 times angle OPQ. So, if OPQ is half of PTQ, that means PTQ is 2 times OPQ. Hence, we have proved the theorem. It's very simple. First, mark the angle as theta. We know that this full angle is 90 degrees. We begin with the isosceles triangle, find out what is this angle, and then subtract it from 90 degrees. So, simple problem. Let's try another one. Let's try this problem. PQ is a chord of length 8 centimeters of a circle of radius 5 centimeter. The tangents at P and Q intersect at point T. Find the length TP. So from the figure, PO is the radius, which is 5 centimeters. PQ is the chord of length 8 centimeters. Observe, if we join OT, R is a point intersecting at PQ, and OR is a line from the center intersecting the chord PQ. So it divides PQ into two equal halves. So PR will be 4 and RQ will also be 4. So let's just write that down over here. So PR, this is going to be 4, and this also will be going to be 4 because PQ will be bisected by OR. Now PRO is a right angle triangle because OR is a perpendicular to PQ. So now in the triangle PRO, if you are looking at the triangle PRO, can we find RO? Of course we can. So RO is going to be equal to square root of PO squared, 5 squared, minus PR squared, which is 4 squared, and that happens to be 3 centimeters. So now we know that RO is 3 centimeters. Let's label TP as X. TP as, this is what we need to find out, because once we find out TP, even TQ is of the same length. So now let's consider the triangle TPR. Let's consider the triangle TPR. Now in the triangle TPR, this triangle, let's label TR as Y because we don't know this. So let's label TR as Y. If this is 90 degrees, this also is 90 degrees. So TPR happens to be a right angle triangle. We can apply the Pythagoras theorem. So according to the Pythagoras theorem, then for the triangle TPR, x squared is going to be equal to y squared plus 4 squared, which is 16. Let's label this as 1. Now let's come to the triangle TPO, the complete triangle TPO. OP is the radius to the tangent. Can you guess what is this angle? It's going to be 90 degrees. So this angle is going to be 90 degrees. So that again happens to be a right angle triangle. TPO happens to be a right angle triangle where we can apply the Pythagoras theorem. Let's apply the Pythagoras theorem for that. So if we apply the Pythagoras theorem for triangle TPO, x squared plus 5 squared will be equal to y plus 3 the whole squared, isn't it? So we have x squared plus 5 squared, that will be equal to the hypotenuse y plus 3 the whole square. Let's label this as our equation 2. Remember what was our equation 1? Our equation 1 was x squared equal to y squared plus 16. That was our equation 1. Let's subtract 1 from 2. So what do we get? If we minus it, if we minus, subtracting 1 from 2, that means equation 2 minus equation 1. So we get x squared cancels, 5 squared will be equal to y plus 3 the whole squared minus y squared minus 16 when you subtract them. So now we can open the brackets. 5 squared is 25. Y plus 3 the whole squared is in the form a plus b the whole squared. So it's y squared plus 9 plus 6y minus y squared minus 16. Plus y squared cancels with minus y squared. So this is going to be 25 equal to 6y minus 7. Simplify it, so we get y will be equal to 32 over 6, which will be, if you further simplify, 16 over 3. So now we know y. We can take the value of y and plug it into equation 1 to find the value of x. Let's do that. So let's plug in the value of y. So x squared will be equal to, y is 16 over 3. So this is 16 over 3 the whole squared plus 16. You can simplify it. X squared equal to, let's keep this as 16 squared over 9 plus 16 over 1. And when you take the LCM of this, it's going to be 9 and 9, making the common denominator. So x squared is going to be equal to 16 over 9 is common over here. So what are we left with? We are left with 16 plus 9. So we have x squared is 16 times 25 over 9. If you only take square roots, x will be equal to 20 over 3. So which is nothing but TP. So a little bit of algebra over here, but simple one. We are only dealing with the Pythagoras theorem. So great going, good efforts, keep trying, practice more number of problems, and this completes the lesson. Thank you very much for watching this video. Please share and subscribe to the channel wisdomoutlined.com. Thank you.